Hello guys. I'm Tim and welcome to our first webinar today on reverse engineering, how attackers uncover secrets in binaries. This is the first webinar in a row that we want to do over the next weeks or months. And today it's the first time also we do it via LinkedIn. So maybe we change it somewhere in the future. We'll try it out. So it's this new playground for us. But now let's start and see how it goes. A few words about me. I'm Tim. I'm the chief scientist and head of engineering and one of the co-founders of mProof, a company based in Germany and Netherlands where we protect embedded firmware against reverse engineering and general cyber attacks. So we basically focus on advancing embedded security solutions. On my own, I have a PhD in binary reverse engineering. And besides, I also give training and lectures at industry conferences at universities. Today, we talk about three things. First, about what is reverse engineering and how and why can this be considered a threat. So, what are motivations behind reverse engineering from a legal and not so legal perspective? And then how can we actually do reverse engineering to extract some secrets in binaries? For that, we will do a practical demonstration and look into how to use Ghidra and other tools to learn about a bit about the internals of a program and to really extract secrets, and also how to patch a binary such that we can modify the program behavior. So let's start. So first, what is reverse engineering? Reverse engineering basically is the extraction of information from a binary program. Let's say we have given a binary blob, which is just a piece of data that we don't know anything about. So like an executable file, like a piece of malware or the Internet Explorer or some embedded firmware, and we want to know what it does. And our goal in understanding what it does can be manifold. For instance, we want to know if we can trust it or not. Maybe it implements some malicious behavior. Maybe we want to ensure that it does what it says that it does. But also from an attacker perspective, maybe we are interested in learning about its internal workings with the goal to find bugs in it that we can exploit it, for instance. Or in the area of industry espionage on competitors, maybe we are interested in looking into what does our competitor do, how does he or she do it, so that we can learn about their internals, their secret source, and maybe re-implement that. Or just dump the firmware, modify a few bits, and put it in another hardware device, or something like that. From a customer point of view, there's also the attack vector of piracy or feature unlocking. Like you have a piece of software that is limited in scope, but the software itself, in theory, supports more functionality. And you, as an end user, want to unlock that. Then you can analyze the code, check how the limitation is realized, and maybe unlock it by modifying parts of the binary. Either way, in many of these reasons, one of the interests is always financial gain. And today we will focus on one sub-aspect of reverse engineering with the goal to get a very short introduction on what is reverse engineering, what's the idea behind that, how does it work, what's the goal, and then we look at it practically from the goal on how we extract and find and extract hard-coded secrets in binaries, be it cryptographic keys, be it serial numbers, be it hard-coded passwords. And then in the second step, we take a look at understanding how code logic works and then we will crack a binary to unlock some additional features that we normally would have to pay off. So, speaking of, let's start and dig onto the details. Let us start with a simple Hello World program. Like if we take a look at a Hello World program, it doesn't really do much magic. So it basically just is a main function and it prints Hello World and then just returns. And this is the original source code. And then this is not the way how it is provided to us. So what a developer, let's say a developer, compiles that with something like that and has a binary. And this binary is then uploaded somewhere and we as end users get this Hello World program. So if we have it, we have a file like that, Hello World. And our goal is now to understand what is this Hello World program, how it is built, how it is realized, and especially what can it do. One thing that we can do is first use a file command. The file command basically checks the first bytes of the program to give us insights about what kind of file it is. Is it a PDF file? Is it a binary executable file? Is it a doc file? Is it a zip file? And what so on. And so now we do file Hello World, and then we see some output that it tells us it's an ELF file, 64-bit for the ARM architecture. So there are a few words we have to think about. First, what is ELF? Then second, what is ARM? And then there are some other things, but let's deal with the first ones. So ELF basically tells us it's an executable for Linux-based systems or Unix-based systems. So this is basically the file format which contains the code, which contains data and other things that are needed, such that this application executes as it needs to execute. And it can print then data and show us things and so on. So, and then this is ELF. Another possibility would be that we see something like PE. PE would be a portable executable. And this would be basically the analog version of an ELF file just for Windows-based systems. So this would be for Windows-based systems, and an ELF file would be for Linux-based systems. Okay, now we know we have an executable file format for Linux. Then it tells us it's ARM64. What is ARM64? Well, we have something which is called a processor architecture. This processor architecture can be, for instance, Intel x86 or x86 64-bit, for instance. Then this is commonly used on desktops and servers. Then we have something which is called ARM64. ARM64 is often used on new Apple devices, but also on smartphones and in general embedded devices. So this is a processor architecture for the mobile embedded world and partially also for the desktop world. Then we could have other architectures like RISC-V or PowerPC or MIPS and so on. So we basically have different implementations and different architectures that support, that can realize or execute code. And it is important that this high-level code, this C code, if we compile it down, it's compiled for one specific architecture, such that it can only execute on a subset of CPUs. And in this case, it is compiled for the ARM 64-bit architecture. And now we have the ARM 64-bit architecture. this can be considered, as all the others, as something which is called ISA. ISA is an instruction set architecture, basically. It defines on the low level how the CPU is organized. For instance, it tells us that we have registers, something like registers to store values. These can be, on the high-level programming language, registers can be understood as a limited set of variables. Then we have instructions to perform arithmetic stuff, like addition, subtraction, multiplication, and so on. And then we have something which is called the instruction set architecture, that basically defines what instructions are supported and how are they decoded. So what does it mean? Well, first, let's go back to this hello world file. This hello world file is a binary file. If we take a look at its binary or hexadecimal representation, like with the hexdump command, and take a look at the hello world, we see that it contains a lot of stuff. This is just in hexadecimal, which doesn't make much usage of for us. So parts of that is the machine code. The machine code is basically the binary basically contains, besides others, contains machine code. And this machine code is the representation of this hello world code for this specific architecture, this ARM 64-bit architecture. And the instruction set architecture basically gives or defines a format how these bytes or these sequences of bytes are decoded into machine instructions. So let's go back to the slides. So here we have just assume a sequence of bytes, and this represents code compiled for a specific instruction set architecture. And now the instruction set architecture defines, for instance, how to read and interpret individual bytes or bits, like what's an addition, what's a multiplication, and so on. We usually go byte by byte. Like, let's assume we have the following decoding scheme, that we have as first parameter the opcode. The opcode is the operation code, which basically tells us which operation to perform, like an addition, a multiplication, or whatever. And then we have a register. The register is, as said, one variable, one kind of low-level variable on the CPU architecture. And a constant can be just a constant which is used as part of the computations. And if you have now a sequence like that, we can, for instance, go byte by byte and say this 0A is decoded to an addition. Because somewhere in the instruction set architecture, which is a large PDF describing how instructions are decoded, it tells us 0A maps to an addition. And then we decode the register, like this 1 would be register 1, or this 2 would be register 2 for this multiplication. And then finally the constant. And the constant is then part of the operand, like this one or this one. And then we would have something which is called assembly code. Assembly code is basically the human-readable form. So now we basically have machine code, and this one is decoded to assembly code. An assembly code is a human-readable form of machine code. And it tells us then something like like if we have a1 0xAA, we can basically read that as R1 is used as R1 plus 0xAA. So basically this constant is added with this operand and the result is stored in this operand here, in this register. Okay, so basically if we come back to this code, we decoded that and now we basically have two instructions decoded. This is what would happen low level natively on the CPU. And we are reverse engineers. We now basically want to start with a binary that we have here, and that we get code, that we have this sequence of bytes somewhere here, and this is that represents code, and we want now know how can we interpret the code, how can we read it. So in theory what we have to do is we have to somehow use a tool that decodes us this code here to a human-readable representation form, like to assembly code. And this tool is called Disassembler. So we have a cool tool called Disassembler, which basically decodes machine code into assembly code. Okay, so basically if we have this code here, or here another blob where we have machine code, and then we put it into a disassembler, we end up with something like that, which is a human-readable form of machine code, and in this term, this is assembly code. And now, if you are more experienced in reading assembly, writing assembly, and stuff like that, you could start analyzing that and understanding what the code does. However, this kind of thing requires some expert knowledge about, you have to know assembly code, you have to have the low-level understanding and so on. So this is not beginner friendly. However, we can improve upon that and automate it in a way that it's still doable and feasible for non-experts. And that's by using another tool, which is called a decompiler. A decompiler basically tries to reconstruct high-level code from machine code. So a decompiler is basically a next step. It takes something like that as input and tries to reconstruct as much as possible high-level code as possible. So for instance, a decompiler might go from something like that to something like that, where we can see the function signature and its function name with two parameters, and then we see that it returns something and the parameters are added together and multiplied by 4. And something like that, it's at least more readable for somebody who doesn't have a reverse engineering background than this one. And now let's assume that you have a binary that you want to analyze, but you are a non-reverse engineering expert. So then it's for sure that you don't want to start here. You instead want to have something which shows you something like that. And this might not be perfect, because maybe it's not perfect like plain C code or something like that. However, it's still a good enough approximation that you can still take something from that or learn something from that without being stuck into all the details of how to read that. And the question is there a tool or is there something that can help you in doing something like that? And the question is yes. So there is a tool, an open source tool called Ghidra. Ghidra is an open source reverse engineering framework written in Java and has been released by the NSA, and it's freely available. So what you can do is you can, for instance, just look for Ghidra download. Then you find it, the homepage here. Then you can go to the GitHub. They could download it, and then you can just start it. And it works on Windows, it works on Linux, it works on Mac OS. I already installed that. So let's start with opening Ghidra. It's this symbol here. So the first thing, if we open Ghidra, it's a bit things to click, but it's doable. So once I open that, it gives me a window like this one. It says it has no active project. What I first have to do is I have to define a project. For instance, I go to File, New Project. It's a non-shared project because I want to reverse engineer on my own. I don't want to contribute with others. And so I give it a name. I just call it webinar reversing. And then I finish. And now I can import a binary. So I go to File, Import File. I would go to Webinars, to the binary, and take this Hello World example here and put it in there. And then it already tells me it's an executable and linkable file format, so it's ELF, and it's AArch64. AArch64 is basically another word for ARM64. So I do OK. And then it gives me more information. I usually just ignore that. And then I double press enter here. And then it launches the analysis tool. It's just on another desktop, so I have to put it on here. It tells me it has not been analyzed. If I want to analyze it, so I press yes. Then it just shows me some things, but I can ignore that. I can just press analyze. And then I get up with a window like that. And here, this looks kind of bloated, but the most important thing for us right now is the right side. The right side is the decompiler output, and here in the middle we see the assembly code. So we see here, this is the assembly code, and if I click somewhere here, I see on the right side decompiler output. And so let's click here. And so it's important, this here is the assembly code. But if you take a look at the right hand side, we see the decompiler output. And here we see that basically we have a function, which this would be the main function. It doesn't have a clear name because the decompiler or the disassembler doesn't know any of the original function names because these information are lost during compilation. So we have now here a function, and we say that it basically puts, which is another API function for printf, prints hello world. And then we return 0. If we compare this with the original code, we see here that we basically have the main function, that we have then a comment, then we have the printf hello world, and we return 0. And if we compile that with the decompiler output here, we can see that we have just some function name. This function name indicates it's just defined after the address where it is layouted in the binary. Then we have the puts or the printf to hello world, and we return 0. So as we can see, it's not perfect. like information like the function name or the comment got lost during compilation, but still, without knowing much about binary analysis, we are just able to put this into Ghidra, and if we find the function here, then we can get a high-level understanding about what the code does. And this is now something, these are now the basics. And now we can build up on that and take a look at a more complicated example that actually is more related to software cracking. So let's take a look at another source file. It's basically license check. So here we have a main function, and this main function reads in a user license. And then it checks if the input license is valid or not. If it's valid, so basically if the user license is valid, then it returns 1, and then it basically unlocks the paid premium feature. Otherwise, it tells us it's an invalid license, access is denied. So, but of course we don't have the source code. So what we have is only the file here, license check. Let's start again checking what kind of file it is. And then again we see it's an ELF file, 64-bit for the ARM architecture. So since this is a Linux, this terminal here is a Linux terminal on ARM 64-bit, I can just execute it. So I can put in license check. And then it tells me, please enter a license. I just put in something and press enter, and then it tells me invalid license, access denied. Okay, so there's currently no way how we can unlock that. We have this file, we can put in something and it tells us access denied. The question is now, how would we unlock this file here? How can we learn the secret? If we take a look at the source code again, you will notice that the correct license is hard-coded in the binary. It's like this ABC 123 XYZ and so on. So basically, if we would input into that, which we don't know, but if we just would put into that, it tells us access granted. Question is now, how do we learn about that? And well, there are multiple ways to that. Let's start with the easy way. So since it's hard-coded, and especially in the embedded security area, we see a lot of things which get hard-coded, like cryptographic keys, hard-coded passwords, and so on, licenses. So we see in the embedded world a lot of things are hard-coded in binaries. And these can be similarly dumped as we do it now. So if we do the hex dump of the license check again, basically looking at the file in hex editor, we can see all the code and its ASCII representation. So somewhere down here is a machine code, that's not interesting to us. But if we scroll up, we see additional information like GCC and some sections that are related to the ELF file. But if we scroll up and up, we also see strings. We see like invalid license key, access denied. This is just something that we saw before as the program output. We see something like enter your license key. This is also something that we saw before. But what we also see is this string ABC123XYZ. So we basically have the credential which is needed to unlock the premium feature hard-coded in the binary. And by just looking at the strings here, we find it somewhere here. There's also another command we could use. We could just use the strings command to the license check, and then we get a list of all strings. And then here we will find that this one is one of them. So question is now, how do we know that this relates to that? Well, we don't know without that. We just might notice that these things are just nearby in the binary, and so maybe we can just try it. But based on that, besides that, we have currently no other way to validate that. However, let's go back to Ghidra again. Now I open not the hello world file, instead I open this license check file. And then I do again import file, the license check, okay. Then I double click here. Then I say yes, analyze, and then it does its magic. And now I have the code here again, but what I can do is I can go to Window and go to strings, define strings. And then on the right side here, I get a list of all the strings in the binary again. And then, for instance, I can go to the access granted, because the access granted is something that I want to reach. And now I see here, somewhere in the data section of the binary, that here I have the access granted. Okay, I know the data, but the most interesting thing is what code parts do interact with the data. And so I can basically look here, they are cross-referenced, which code parts interact with the data. And I can click on that. And then I look in the decompiler output again. And now I see here we have something like enter your license key. Then we put in the license key here. Then we perform a check with something like that. And then if this holds, it tells us access granted. The premium is now unlocked. Otherwise, invalid license access denied. Okay, so this seems to be related to that. So this does not really help us a lot, because what is that? But we at least can see the high-level logic. So what else can we do is we can go back to the defined strings and look at the string we just saw before, this one here, and see, here we see that this is also used, this ABC 1, 2, 3, that this is also used somewhere in the binary. So we can click on that and go to the decompile again, and we see, oh, this seems to be somehow related here. We don't see it immediately in the decompiler output, but here we see that this is the A and this is XYZ. So we might come, at least without diving too much into the details, we might just at least come to the idea that this might be related, and then that we can take a closer look and that we have to put it into here. Especially if we know that here we have that this looks like printable ASCII characters, like 41, 42, 43. If you take a look at an ASCII table, let's take a look at an ASCII table. if we take a look at 0x for 1, for 2, for 3, we see that this is A, B, C. So we at least learn that this seems to be somehow related to that. And then we can come up with, oh, this might be the case. Okay. What else we could do is, we could try another decompiler or another tool. Maybe it gives us more information. So Ghidra, as said, Ghidra is open source and provides a lot of information. However, there are other tools like Binary Ninja, which are paid, which also exist in paid versions, but there also exists a free version or a cloud-based version. So, and we can download this one and also open the binary with that and see what's going on. So let me just do that. I go to the webinars folder. I open the binary, the license check. And there again, I have now here immediately the decompiler output of the main function. And here it tells me, here at least I see that I do some form of string copy. And then based on the string copy, I copy the ABC minus until the X. So at least this again seems somehow related. We see that the decompiler output does not perfectly reconstruct it, but it still reconstructs the high-level structure quite well. Like enter your license key, then the scanf, then the checks, and the checks tell me access granted or invalid license. If I compare that with the original one, I can see here I have the check license, and then it unlocks the features, and the check license works like that. So probably due to compiler optimizations, this check license has been inlined into the main function. Okay, given that, we now have a better understanding of how we could approach that. Let us go and basically extract a hard-coded secret to unlock premium features. Let us go one step further without looking at the code. So now we have a small game. And let's first start again the game. It's again an ELF Linux 64-bit. So we can execute it. Let's execute that. And then it's basically tells us enter your license key or type trial for limited trial. I just do nothing. I just put in ABCD or whatever. And it tells me it's an invalid license, access denied. Okay, let me put in trial. And then it's a number guessing game. I have to guess a number between 1 and 100. And I only have 3 attempts in this trial number, in this trial version. So I can put in, let's say, 5, 2, and 7. And after the 3 trials, it tells me, sorry, I've used everything, so I didn't approach it correctly. Okay, so the question is here again, what would be a valid user, a valid serial that allows me to bypass this trial? So to approach that, again, I can just look at the strings. I can look at the strings, and then I scroll up a bit, and then here I find something like trial mode, you have 3 attempts, then full access granted, and so on. And I have a string here which looks kind of suspicious. Game unlock minus 2024. Let's try that. So let's do here. Then let's do game unlock 2024. and then it tells me full access granted. Now I have an unlimited number of attempts. So I can put in whatever I want here, and after 3 trials, it still works. So now, based on interacting with the program and looking at the strings, I found the valid license. Again, I could put into Ghidra. Let's do that again. Like loading the game into Ghidra, then analyzing it, then we look at the defined strings, and then we look for something which is called full access granted. Here we then see, oh, this is the point we want to reach. It's in the main. We check the decompiler again. And then we see, quite similar from before, we have this printf here. Then we read in the scanf. Then it basically tells me if it's correct, it's full access granted. Otherwise, it tells me you have an unlimited number of attempts, and it's fine. Otherwise, it's a trial mode. Okay. And here again, if I take a look in the code somewhere, like in the defined strings, there should also be this game unlock here. And I've checked whether the game unlock is used. Decompiler. I basically see, oh, there's a call to a function called check license. And here it's basically just like a string compare with a provided parameter and game unlock 2024. And if you take a look at the code now, we basically see that we have check license, which takes in an input license and a correct license, which is hard-coded to game unlock 2024. It then tells me that it's based on string compare 1. Okay, so that's something I reconstructed by looking at the code with Ghidra. So now let's recap. If we took a look at the slides, so we basically talked about finding hard-coded secrets in binaries. In this case, it was focused on serial numbers, but cryptographic keys and passwords would work in a very similar way. Now let's go to the second part, to the second step, how we can crack the software to unlock premium features. For that, our goal is to rewrite. So basically our goal is to rewrite the software, or to crack the software such that it accepts any license. This would be our goal. And then, how? The idea is basically we rewrite the machine code with other machine code. We basically change the control flow logic. If we take a look at the source code, we see that we have here if check license, then we basically only then we apply that, otherwise that. So now we would basically want to get rid of this if then else and modify it in a way that we do like if true and remove the check license part, then we just do the printf. Something like that. That we basically remove the license part such that we always access that. This would be our goal. We can do this in Ghidra. In Ghidra, we have the option, for instance, to patch an instruction and modify that, but this requires a bit more low-level experience with Ghidra to do it. If we do it with Binary Ninja, it's significantly more easy to patch a binary. So, for instance, we could open the game, and here we see again, this is our goal. This is basically our binary. This is the check where we validate the license, and then it prints full access granted. If we switch the view by pressing space, we have something which is known as control flow graph, which basically shows us the high-level structure of the function, so like the program flow logic. If we have two edges outgoing, it tells us it's basically an if then else, like we can see here. And so what we want to do is basically that we always accept. So what we could do is basically press here after inputting the serial. We could just press something like patch always branch. If we then look at the decompiler output, we see that we will always go to this state. This is not what we intended for. So instead, what we can do is we can do something as never branch. Then it checks mainly for the trial mode. This is also not what we intended. So what we have to do is we have to basically always go here and then never go here. So what I could do is I could just patch and then always branch, that we always go here. And then we want to always go to the false case. False means red branch. So we can put it here and then go to patch and never branch. And now, if you take a look at the decompiler output, we see that it just always accepts. And this is now rewritten, the code, and we have to patch it to the binary. So we can do file, save as, file contents, and then we put it like game patched. And then we have a new file here, the file game patched. If I make it executable and execute it, I can now put in whatever I want, and it tells me full access granted. You have unlimited number of access. And then I can just put in here and it's fine. So this was the hard part, where I took a look at the code logic, tried to understand it, and then patched a few branches such that I can patch out the check forever. However, there's another thing I could patch. So if I take a look at how the code is defined, I see that the number of trial users is hard-coded to 3. And nobody enforces me to leave it to 3. I can change this arbitrarily. So remember, in the original binary right now, if I put in trial, I just have 1, 2, 3, and then it terminates. So now my goal is to increase the number there. What I do is, again, I go back to game, and here I have a variable trial users, which is set to 3. I can switch to the hexaditor view. Then I have this 3 here. And then I can just change this to some arbitrary value. Let's put a 7 in there. Like 07. This was this one. Let's go 07. Now I patched it with 7. Like if I now look at the code, I see the trial users is set to 7. If I patch it now, like save as, save contents, and I rename it to game patched 2, and I make it executable, and I execute it. Now, if I put in trial, it tells me I have 3 attempts because I didn't change the string. But if I put in now 1, 2, 3 numbers, you see it doesn't terminate. But 5 or 4, 5, 6, and then it terminates. So instead of patching the control flow logic, I was able, by looking at the decompiler, how the code works, like this one here, and then I saw, oh, this trial user seems to be hard-coded. And then I can just increase the number here to some arbitrary number. And this way, the same process works perfectly. So, to sum up, from a reverse engineering point of view, we can first, if we want to bypass, like we discussed, like extracting secrets, especially for piracy and feature unlocking, we can look for hard-coded secrets in binaries, like cryptographic keys, serial numbers, or passwords, and then extract them. Or another way we can do is that we can really crack the software to modify some data or modify the control flow such that we can unlock premium features. So if you want to do this on your own, so basically we discussed how we can do reverse engineering to extract secrets from binaries. There are powerful tools out there like Ghidra, which is freely available and open source, or Binary Ninja, or IDA, where free versions are available. So you can find them. For the low-level part, you of course need some knowledge, but just to work with the decompiler, it gives you in many cases a lot of understanding of the code and helps you in a lot of cases too, without having a deep knowledge. So, and these are just freely to download. So if you want to try it on yourself, on your own, you can visit this link. Then you will find Improve webinar page. Like this one here. There you will find a list, an overview of our webinars, which is the first one today. You will see the recording, so this will be uploaded in the next days on YouTube and linked here. But if you click on this folder, then you will find not only the abstract from today, but also the slides from today. And most importantly, you will find the source code of the samples and the binary executables compiled for Linux 64-bit ARM, such that you can repeat everything on your own. So I hope this was, you learned something and you found it interesting. If you have more questions about that, just reach out. if you want to learn what you can do to protect against reverse engineering, like for instance your embedded firmware or something like that, check out our homepage, Improve, because we build products that prevent reverse engineering or make reverse engineering more infeasible for attackers by adding protection against various attack vectors there. So yeah, I hope you learned something. If you're interested trying it on your own, just do it. Everything is freely available here. If you want to learn about how to protect against it, check out Improve. Otherwise, thanks a lot. The webinar will be uploaded, the slides will be uploaded. I will send it around later today or tomorrow. And are there any additional questions? I just noticed I have a chat here. I didn't see the chat before. Okay, doesn't seem like any questions. So if you come up with questions afterward, just drop me a mail or something like that. I'm happy to answer. And otherwise, thanks a lot for your interest and your time. And we will see each other somewhere on the world, in the internet. Thanks a lot. Have a good day.